from its history to its potential for being a base for humanity and more. Join us as we explore Phobos, Mars's moon. Number 7. History of Phobos. Phobos was discovered by astronomer Asaph Hall on August 18, 1877 at the United States Naval Observatory in Washington, D.C. at about 9:14 Greenwich Mean Time. Contemporary sources using the pre-1925 astronomical convention that began the day at noon give the time of discovery as August 17, 1606 Washington Mean Time, meaning August 18, 406 in the modern convention. Hall had discovered Deimos, Mars's other moon, a few days earlier on August 12, 1877 at about 7:48 UTC. The names, originally spelled Phobos and Deimos respectively, were suggested by Henry Madan, 1838 to 1901, science master at Eton College, based on Greek mythology, in which Phobos is a companion to the god Eris. Speculation about the existence of the moons of Mars had begun when the moons of Jupiter were discovered, when Galileo Galilei, as a hidden report about him having observed 2 bumps on the sides of Saturn, later discovered to be its rings. Hall recorded his discovery of Phobos in his notebook as follows: I repeated the examination in the early part of the night of 11th August 1877, and again found nothing. But trying again some hours later, I found a faint object on the following side and a little north of the planet. I had barely time to secure an observation of its position when fog from the river stopped the work. This was at 2:30 o'clock on the night of the 11th. Cloudy weather intervened for several days. On 15 August, the weather looking more promising, I slept at the observatory. The sky cleared off with a thunderstorm at 11 o'clock, and the search was resumed. The atmosphere, however, was in a very bad condition, and Mars was so blazing and unsteady that nothing could be seen of the object, which we now know was at that time so near the planet as to be invisible. On 16 August, the object was found again on the following side of the planet, and the observations of that night showed that it was moving with the planet, and if a satellite was near one of its elongations. Until this time, I had said nothing to anyone at the observatory of my search for a satellite of Mars, but on leaving the observatory after these observations of the 16th, at about 3 o'clock in the morning, I told my assistant George Anderson, to whom I had shown the object, that I thought I had discovered a satellite of Mars. I told him also to keep quiet, as I did not wish anything said until the matter was beyond doubt. He said nothing, but the thing was too good to keep, and I let it out myself. On 17 August, between 1 and 2 o'clock, while I was reducing my observations, Professor Newcomb came into my room to eat his lunch, and I showed him my measures of the faint object near Mars, which proved that it was moving with the planet. On 17 August, while waiting and watching for the outer moon, the inner one was discovered. The observations of the 17th and 18th put beyond doubt the character of these objects, and the discovery was publicly announced by Admiral Rogers. Number 6. Orbits and rotations. The orbital motion of Phobos has been intensively studied, making it the best studied natural satellite in the solar system in terms of orbits completed. Its close orbit around Mars produces some unusual effects. With an altitude of 5,989 kilometers, or 3,721 miles, Phobos orbits Mars below the synchronous orbit radius, meaning that it moves around Mars faster than Mars itself rotates. Therefore, from the point of view of an observer on the surface of Mars, it rises in the west, moves comparatively rapidly across the sky in 4 hours, 15 minutes or less, and sets in the east approximately twice each Martian day, every 11 hours and 6 minutes. Because it is close to the surface and in an equatorial orbit, it cannot be seen above the horizon from latitudes greater than 70.4 degrees. Its orbit is so low that its angular diameter, as seen by an observer on Mars, varies visibly with the position in the sky. Seen at the horizon, Phobos is about 0.14 degrees wide. At zenith, it is 0.20 degrees, 1/3 as wide as the full moon is seen from Earth. By comparison, the Sun has an apparent size of about 0.35 degrees in the Martian sky. Phobos's phases, in as much as they can be observed from Mars, take 0.3191 days, Phobos' synodic period, to run their course, a mere 13 seconds longer than Phobos' sidereal period. As seen from Phobos, Mars would appear 6,400 times larger and 2,500 times brighter than the full moon appears from Earth, taking up a quarter of the width of a celestial hemisphere. An observer situated on the Martian surface, in a position to observe Phobos, would see regular transits of Phobos across the Sun. Several of these transits have been photographed by the Mars rover Opportunity. During the transits, Phobos' shadow is cast on the surface of Mars, an event which has been photographed by several spacecraft. Phobos is not large enough to cover the Sun's disk and so cannot cause a total eclipse. Number 5. Surface. Phobos and Deimos appear to be composed of C-type rock, similar to blackish carbonaceous chondrite asteroids. Observations by Mars Global Surveyor indicate that the surface of this small body has been pounded into powder by eons of meteoroid impacts, some of which started landslides that left dark trails marking the steep slopes of giant craters. Measurements of the day and night sides of Phobos show such extreme temperature variations that the sunlit side of the moon rivals a pleasant winter day in Chicago, while only a few kilometers away on the dark side of the moon, the climate is more harsh than a night in Antarctica. High temperatures for Phobos were measured at 25 degrees Fahrenheit, -4 degrees Celsius, and lows at -100 degrees Fahrenheit, -112 degrees Celsius. This intense heat loss is likely a result of the fine dust on Phobos' surface, which is unable to retain heat. Before we continue to break down Phobos, be sure to like or dislike the video so that we can continue to improve our content for you, the viewer. Also be sure to subscribe so that you don't miss any of our weekly videos. Number 4. Controversial origin. The origin of the Martian moons is still controversial, which is interesting given how long we've been studying them. Phobos and Deimos both have much in common in regards to their composition and even their shape and size in certain areas. Based on their similarity, one hypothesis is that both moons may be captured main belt asteroids. Both moons have very circular orbits which lie almost exactly in Mars' equatorial plane, and hence a capture origin requires a mechanism for circulating the initially high eccentric orbit and adjusting its inclination to the equatorial plane, most probably by a combination of atmospheric drag and tidal forces. Although it is not clear that sufficient time is available for this to occur for Deimos, capture also requires dissipation of energy. The current Martian atmosphere is too thin to capture a Phobos-sized object by atmospheric braking. Jeffrey A. Landis has pointed out that the capture could have occurred if the original body was a binary asteroid that separated under tidal forces. Phobos could be a second-generation solar system object that coalesced in orbit after Mars formed, rather than forming concurrently out of the same birth cloud as Mars. Another hypothesis is that Mars was once surrounded by many Phobos and Deimos-sized bodies, perhaps ejected into orbit around it by a collision with a large planetesimal. The high porosity of the interior of Phobos is inconsistent with an asteroidal origin. Observations of Phobos in the thermal infrared suggest a composition containing mainly phyllosilicates, which are well known from the surface of Mars. The spectra are distinct from those of all classes of chondrite meteorites, again pointing away from an asteroidal origin. Both sets of findings support an origin of Phobos from material ejected by an impact on Mars that reaccreted in Martian orbit, similar to the prevailing theory for the origin of Earth's moon. The irony here is that it's hard to tell which of these theories is true, especially since we're still evaluating the origins of Mars itself. Only through various tests on both the planet and the moons can we likely find the truth of what is going on. Number 3. Could Phobos be hollow? If it's not clear by now, Phobos is a very unique moon compared to many of the others within our solar system, but one man has noted that there may just be a unique way of explaining it all. Mainly, this person believes that Phobos could be hollow. Around 1958, Russian astrophysicist Iosif Samuelovich Klovsky, studying the secular acceleration of Phobos' orbital motion, suggested a thin sheet metal structure for Phobos, a suggestion which led to speculations that Phobos was of artificial origin. Shklovsky based his analysis on estimates of the upper Martian atmosphere density and deduced that for the weak braking effect to be able to account for the secular acceleration, Phobos had to be very light. One calculation yielded a hollow iron sphere 16 kilometers, 9.9 miles across, but less than 6 centimeters thick. In a February 1960 letter to the journal Astronautics, Fred Singer, then science advisor to U.S. President Dwight D. Eisenhower, said of Shklovsky's theory, "If the satellite is indeed spiraling inward as deduced from astronomical observation, then there is little alternative to the hypothesis that it is hollow and therefore Martian-made. The big if lies in the astronomical observations. They may well be in error, since they are based on several independent sets of measurements taken decades apart by different observers with different measurements. Systematic errors may have influenced them. These errors were indeed found, and later observations and investigations revealed that Phobos is a kind of rubble pile moon. In addition, images obtained by the Viking probes in the 1970s clearly showed a natural object, not an artificial one. Nevertheless, mapping by the Mars Express probe and subsequent volume calculations do suggest the presence of voids and indicate that it is not a solid chunk of rock, but a porous body. So while it was a curious theory, and one that would have rewritten history, it was not one that was proven to be true by any metric. Number 2. Could Phobos be destroyed via natural patterns? Tidal deceleration is gradually decreasing the orbital radius of Phobos by 2 meters every 100 years. Scientists estimate that Phobos will be destroyed in approximately 30 to 50 million years, with one study's estimate being about 43 million years. Phobos's grooves were long thought to be fractures caused by the impact that formed the Stickney crater. Other modeling suggested since the 1970s support the idea that the grooves are more like stretch marks that occur when Phobos gets deformed by tidal forces. But in 2015, when the tidal forces were calculated and used in a new model, the stresses were too weak to fracture a solid moon of that size, unless Phobos is a rubble pile surrounded by a layer of powdery regolith about 100 meters or 330 feet thick. Stress fractures calculated for this model line up with the grooves on Phobos. The model is supported with the discovery that some of the grooves are younger than others, implying that the process that produces the grooves is ongoing. Given Phobos's irregular shape and assuming that it is a pile of rubble, specifically a more Coulomb body, it will eventually break up when it reaches approximately 2.1 Mars radii. When Phobos is eventually torn apart by tidal forces, a fraction of the debris will likely form a planetary ring around Mars, which may last from 1 million to 100 million years. A very interesting end for a very interesting moon. Number 1. Colony on Phobos? As you all likely know, both NASA and SpaceX are preparing themselves for a mission of grand importance. They're going to try and colonize Mars. This mission will take many years to fully complete, and launch for the first part will be in the next few years. But many are already planning for what is to come after we truly make contact on Mars. Mainly once the main colony is set up, we'll immediately start expanding. Now, the initial thought is to go to another planet to colonize, or a moon of a planet beyond Mars. But many are thinking that Mars could be a perfect launch point for a set of colonies. Mainly have a main one on Mars to start, and then have waypoint stations on Phobos and Deimos. But why do that? Because it would allow for easier transition both in and out of Mars's atmosphere, which is thin but still there, and its gravity pull. There are some who even speculate that a certain kind of perpetual motion machine can be put on the moons to help launch ships into the asteroid belt area that separates Mars and Jupiter, and thus make it easier to get into the back half of the solar system. Plus, having bases on the moons could allow for travel between Earth and Mars and beyond, as well as potentially setting up mining stations for going into the asteroid belt and seeking out materials there. Granted, this is a lot of theories at the current moment, however, there are plans in motion that could make this happen. The only question is how soon this could potentially happen, which obviously will be decided based on the main Mars mission. From its size and shape to its orbit, to how it might further humanity across the stars, join us as we explore Deimos, Mars's moon. Number 8. History. Deimos was discovered by Asaph Hall III at the United States Naval Observatory in Washington, D.C. on August 12, 1877 at about 7:48 UTC, given in contemporary sources as August 11, 1440, Washington Mean Time, using a pre-1925 astronomical convention of beginning a day at noon. So 12 hours must be added to get the actual local mean time. Hall also discovered Phobos on August 18, 1877 at about 9:14 GMT, after deliberately searching for Martian moons. It is named after Deimos, a figure representing dread in Greek mythology. The names at first spelled Phobos and Deimus were suggested by Henry Madan, 1838 to 1901, science master of Eton, from Book 15 of the Iliad, where Eris, the Roman god Mars, summons dread, Deimos, and fear, Phobos. Hall recorded his discovery of Phobos in his notebook as follows: I repeated the examination in the early part of the night of 11th August 1877, and again found nothing. But trying again some hours later, I found a faint object on the following side and a little north of the planet. I had barely time to secure an observation of its position when fog from the river stopped the work. This was at 2:30 o'clock on the night of the 11th. Cloudy weather intervened for several days. On 15 August, the weather looking more promising, I slept at the observatory. The sky cleared off with a thunderstorm at 11 o'clock, and the search was resumed. The atmosphere, however, was in a very bad condition, and Mars was so blazing and unsteady that nothing could be seen of the object, which we now know at the time was so near the planet as to be visible. On 16 August, the object was found again on the following side of the planet, and the observations of that night show that it was moving with the planet, as if a satellite was near one of its elongations. Until this time, I had said nothing to anyone at the observatory of my research for a satellite of Mars. But on leaving the observatory after these observations of the 16th, at about 3 o'clock in the morning, I told my assistant George Anderson, to whom I had shown the object, that I thought I had discovered a satellite of Mars. I told him also to keep quiet, as I did not wish anything said until the matter was beyond doubt. He said nothing, but the thing was too good to keep, and I let it out myself. On 17 August, between 1 and 2 o'clock, while I was reducing my observations, Professor Newcomb came into my room to eat his lunch, and I showed him my measures of the faint object near Mars, which proved that it was moving with the planet. On 17 August, while waiting and watching for the outer moon, the inner one was discovered. The observations of the 17th and 18th put beyond doubt the character of these objects, and the discovery was publicly announced by Admiral Rogers. Number 7. Orbits and rotations. Deimos' orbit is nearly circular and is close to Mars' equatorial plane. Deimos is possibly an asteroid that was perturbed by Jupiter into an orbit that allowed it to be captured by Mars, though this hypothesis is still controversial and disputed. Both Deimos and Phobos have circular orbits which lie almost exactly in Mars' equatorial plane, and hence a capture origin requires a mechanism for circulating the initially high eccentric orbit and adjusting its inclination into the equatorial plane, most likely by a combination of atmospheric drag and tidal forces. It is not clear that sufficient time was available for this to have occurred for Deimos. As seen from Mars, Deimos would have an angular diameter of no more than 2.5 minutes. 60 minutes make 1 degree. 1/12 of the width of the Moon is seen from Earth, and would therefore appear almost star-like to the naked eye. At its brightest, full moon, it would be about as bright as Venus is from Earth. At the first or third quarter phase, it would be about as bright as Vega. With a small telescope, a Martian observer could see Deimos' phases, which take 1.2648 days, Deimos' synodic period, to run their course. Unlike Phobos, which orbits so fast that it rises in the west and sets in the east, Deimos rises in the east and sets in the west. The Sun's synodic orbital period of Deimos is about 30.4 hours, exceeds the Martian solar day, Sol, of about 24.7 hours, by such a small amount that 2.48 days, 2.41 sols, elapse between its rising and setting for an equatorial observer. From Deimos rise to Deimos rise, or setting to setting, 5.466 days, 5.320 sols, elapse. Because Deimos' orbit is relatively close to Mars and has only a very small inclination to Mars's equator, it cannot be seen from Martian latitudes greater than 82.7 degrees. Deimos' orbit is slowly getting larger because it is far enough away from Mars and because of tidal acceleration. It is expected to eventually escape Mars's gravity, which is in contrast to Phobos, who is having its orbit degraded every 100 years, and is expected to be destroyed by Mars eventually and then become its ring. Number 6. Size and structure. Deimos is the smaller of Mars's two moons, being only 9 by 7 by 6.8 miles in size, 15 by 12 by 11 kilometers. Like Phobos, Deimos is a small and lumpy, heavily cratered object. Its craters are generally smaller than 1.6 miles or 2.5 kilometers in diameter. However, it lacks the grooves and ridges seen on Phobos. Typically, when a meteorite hits a surface material is thrown up and out of the resulting crater. The material usually falls back to the surface surrounding the crater. However, these ejected deposits are not seen on Deimos, perhaps because the moon's gravity is so low that the ejecta escape to space. Material does not appear to have moved down slopes. Deimos also has a thick regolith, perhaps as deep as 328 feet or 100 meters, formed as meteorites pulverize the surface. Deimos is a dark body that appears to be composed of C-type surface materials, similar to that of asteroids found in the outer asteroid belt. Number 5. Exploration. Not surprisingly, the exploration history of Deimos is similar to those of Mars and Phobos. Deimos has been photographed in close-up by several spacecraft, whose primary mission has been to photograph Mars. No landings on Deimos have been made. The Soviet Phobos program sent 2 probes to Phobos. In case Phobos 1 succeeded, Phobos 2 could have been sent to Deimos. Both probes launched successfully in July of 1988. The first was lost en route to Mars, whereas the second returned some data and images, but failed shortly before beginning its detailed examination of Phobos' surface, including a lander. In 1997 and 1998, the proposed Aladdin mission was selected as a finalist in the NASA Discovery program. The plan was to visit both Phobos and Deimos and launch projectiles at the satellites. The probe would collect the ejecta as it performed a slow flyby, around 1 kilometer per second. These samples would be returned to Earth for study 3 years later. The principal investigator was Carl M. Peters of Brown University. The total mission cost, including launch vehicle and operations, was $247.7 million. Ultimately, the mission chosen to fly was Messenger, a probe to the planet Mercury. In 2008, NASA Glenn Research Center began studying a Phobos and Deimos sample return mission that would use solar electric propulsion. The study gave rise to the Hall mission concept, a New Frontiers-class mission currently under further study. Also, the sample return mission called Gulliver has been conceptualized and dedicated to Deimos, in which 1 kilogram, 2.2 pounds, of material from Deimos would be returned to Earth. Another concept of sample return mission from Phobos and Deimos is OSIRIS-REx 2, which would use heritage from the first OSIRIS-REx. In March 2014, a Discovery-class mission was proposed to place an orbiter on Mars orbit by 2021 and study Phobos and Deimos. It is called Phobos and Deimos and Mars Environment, PADMA. Human exploration of Deimos could serve as a catalyst for the human exploration of Mars. Recently, it was proposed that the sands of Deimos or Phobos could serve as a valuable material for aerobraking in the colonization of Mars. Because the small Delta V budget of Phobos, a small amount of chemical fuel brought from Earth could be transformed in a very large amount of sand lifted from the surface of Phobos, from a permanent outpost to a transfer orbit. This sand could be released in front of the spacecraft during the descent maneuver, and then resulting in a desensification of the atmosphere just in front of the spacecraft. Number 4. Solar transits. Deimos regularly passes in front of the Sun as seen from Mars. It is too small to cause a total eclipse, appearing only as a small black dot moving across the Sun. Its angular diameter is only about 2.5 times the angular diameter of Venus during a transit of Venus from Earth. Its fellow moon, Phobos, also has a similar kind of solar transit because it is too small that it can't block out the Sun. However, it still creates quite the interesting image. On March 4, 2004, a transit of Deimos was photographed by Mars rover Opportunity, and on March 13, 2004, a transit was photographed by Mars rover Spirit. Number 3. Controversial origins. The origin of the Martian moons is still controversial, which is interesting given how long we've been studying them. Phobos and Deimos both have much in common in regards to their composition and even their shape and size in certain areas. Based on their similarity, one hypothesis is that both moons may be captured main belt asteroids. Both moons have very circular orbits which lie almost exactly in Mars's equatorial plane, and hence a capture origin requires a mechanism for circularizing the initial highly eccentric orbit and adjusting its inclination to the equatorial plane, most probably by a combination of atmospheric drag and tidal forces, although it is not clear that sufficient time is available for this to occur for Deimos. Capture also requires dissipation of energy. The current Martian atmosphere is too thin to capture a Phobos-sized object by atmospheric braking. Jeffrey A. Landis has pointed out that the capture could have occurred if the original body was a binary asteroid that separated under tidal forces. Another hypothesis is that Mars was once surrounded by many Phobos and Deimos-sized bodies, perhaps ejected into orbit around it by a collision with a large planetesimal. The impact on Mars that reaccreted in Martian orbit would be similar to the prevailing theory for the origin of Earth's moon, in which many people believe that a large object smashed into the Earth and the remnants of that impact were caught in the gravity of the Earth and eventually formed into the moon. The irony here is that it's hard to tell which of these theories is true, especially since we're still evaluating the origins of Mars itself. Only through various tests on both planet and the moons can we likely find the truth of what is going on. Number 2. Odd shape. Go ahead and picture in your mind a moon. More than likely you went and pictured the moon that is orbiting the Earth right now, which is fair. When you think of a moon, you no doubt think of a perfectly spherical object, perhaps one that has a lot of craters like the Earth's moon. But when you look at Deimos, as well as its partner Phobos, you'll notice that these moons aren't regular-shaped moons. In fact, if you look at Deimos especially, you'll see various dips in its contour that makes it feel more like an asteroid than a regular moon, which again backs up the origin theories that were stated. This is curious for all sorts of reasons, not the least of which is that you could argue that Deimos is one of the oddest moons in the solar system simply because of its shape. Number 1. Colony material? While the world today doesn't seem like a very hopeful place, there are those who are striving for certain goals in the current decade that can elevate humanity as a whole. And the biggest of those goals is starting the Mars colony. Whether it's by SpaceX or NASA, man is likely going to set foot on the moon this decade. But what happens after that colony is started up? Well, many have asked that question, and many feel that it is very likely that either Phobos or Deimos could be tapped as special waypoint stations or mini colonies for Mars. The applications of these moons could be diversified based on the needs of the main colony, or the desire to further explore into the outer reaches of the solar system. The intent here in many people's minds is to not burden the main Mars colony too much. By putting colonies on the moons, it could act as a buffer to bring in supplies, or allow for easier launches into space, as they'd be truly launching off the moon instead of shooting right into space from Mars. There are a lot of ways this could work. It would just be a matter of intent, time, money, and the ability to build it on the irregular moons.